Hi, and welcome to Gaffy's Grinds. In this video, we are continuing our exam question walkthroughs for the titration questions. So this is the higher level question from 2017. On a higher level, the titration is almost always question one. So without any further ado, we're going to jump into this. Okay, we should know what we need to do this question to work through this with me by now, if you've been watching all the other videos. What I'm going to ask you to do, I'm going to ask you to pause the video, find your exam papers and read along through this important piece of text here and see can you pick out the important information. Okay, so hopefully you've had a read of that now. Remember, the higher level, this is the extra challenge, is how the information is given to you and how you pick out and solve the problems that they're providing you with. First of all, I see a formula here. I think that this is going to be important later on. So this substance is called hydrated ammonium iron 2 sulfate. So this was one of the titrations where we did this here as a source of iron, as you can see down here in our chemical equation. This provides the iron, and we react it with that nice purple solution of potassium permanganate, and we react them together in a titration. Okay, so that's going to be important later on, I think. It says it's used as a primary standard. So I'm guessing you guys should remember what that is. It's one of our definitions. And it was prepared, so this is how we made it up, by providing 8.82 grams of crystals in dilute sulfuric acid and making a solution up to 250. Okay, so that's going to give us some context later on, I think. We've got 8.82 grams of crystals in a quarter of a liter and 250 cm cubed. This was now a standard solution, is what it says here. This was a standard solution, so that's important too. And it's underlined, which probably means we're going to have to explain what that means later on, and was titrated in 25 centimeters cubed portions. So that means the standard solution, which was the iron, was in 25 centimeters cubed portions, to which some more dilute sulfuric acid had been added with a solution of potassium permanganate. So the potassium permanganate was the other solution. And it says here on average, 20.45 centimeters cubed of the potassium permanganate were required to completely oxidize the iron ions. So in other words, when we were doing the titration, this amount of potassium permanganate was required for this amount of the iron solution. That's per titration. Right, so that's the important pieces of information in the text. Hopefully you highlighted all of that stuff as being, we're probably going to need that later on. Let's jump into the questions. So A part one, a lot of the early stuff in these questions does be just theory. So it says explain the underlying term. So what you have to do is explain the definition for a standard solution. What is a standard solution? Explain what it is. And then for part two of A, it says give two essential properties of a primary standard for volumetric analysis. So you should know that we use only chemicals that are primary standards to make standard solutions. What are some of the features or properties that a chemical has to have to call it a primary standard? So pause the video and explaining that now. So standard solution and what are the properties of primary standards? Pause the video and write down your answers to those now, please. Doing that now. Okay, let's go to the marking scheme now for your correct answers here. It's just my page is frozen here. Give me a second to sort this out. I'm just going to pause for a second. And welcome back. Apologies about that. So first thing is explain a standard solution. It's a solution whose concentration we know. Okay, so it's a solution of known concentration. Again, key bit here in bold, you have to have that the concentration is known. So if you have that, well done, give yourselves marks. If not, guys, then I suggest you find a way of learning your definitions. As a teacher, it's my job to explain to you what a standard solution is, and I hope that I've done that for my students. But then after that, you guys have to find a way to practice those definitions so that you know them, okay? So I suggest flashcard method, some way of self-quizzing yourself with them, practicing self-quizzing. Okay, what are the features of a primary standard? Okay, so for a primary standard, it has to be pure, soluble, solid, and stable. Okay, there's four there. Any three of them get you the marks. All right. There's lots of other things as well down here, but I always get my students to say pure, stable, soluble. Pure, stable, and soluble. That's basically what they have to be. All right. So give yourselves any two correct ones. Give yourselves 3 marks each. All All right, so we'll not spend any more time on that because that's pretty just straightforward theory. Let's move on to part B. Okay, so here we're going to move on to part B. B part 1. What does it say? Explain why it was necessary. Okay, so explain why it was necessary. And we're going to be talking about the acid that we added. We added acid in 2 places. Why did we add sulfuric acid when we were preparing the solution? So we dissolved the ammonium iron 2 sulfate crystals into acid first and then made it up with water. Why did we add the first portion of acid? First acid. What was the reason for that? Pausing the video and answering that now. And then it says why was it necessary to add more dilute sulfuric acid to each 25 centimeter cube portion of the standard solution used in the titrations? So this is part 2. Why did we add more sulfuric acid just before the titration, the second portion of acid? Again, this is theory. I explained this at the time for my students. You guys then have to learn those reasons why and find a way of remembering this stuff. Okay, so let's go to the mountain scheme again. Hopefully you should only be playing if you've answered this. So if we don't add iron to the crystals when we're making up the solution, they will oxidize with the air. Fe2 plus will oxidize with air. Okay, so the reason why we're doing this is to prevent oxidation of the iron 2 or with oxygen either in the air or in water if we put it straight into water. So that's what we're trying to do, prevent oxidation from iron 2 plus to iron 3 plus. Why do we want to do that so bad? Well, if iron 2 plus oxidizes to iron 3 plus before we get it in the solution, this will not react with potassium permanganate. So therefore, when we add the potassium permanganate, there won't be enough, or there won't be any iron 2 there, and the reaction isn't going to work. We need it for iron. We need it to be iron 2 so that the KMnO4 can react with it. If it's not, then it won't. So it'll be a waste of time doing the titration. So we need to prevent oxidation by the air of Fe2 plus to Fe3 plus. What about the second one? The second one, what we want to happen is we want Mn, which is in the KMnO4. This manganese in this state is in the +7 oxidation state. This is purple. And what we want to do is we want to fully reduce it down to Mn plus 2, which is colorless at the end. That's what we want to happen. We want a full reaction or a full reduction of Mn2 plus 7 to Mn plus 2. If we don't add some acid, what ends up happening is the Mn goes to a +4 oxidation state, which is a dirty brown colored solid. So if we don't add the second portion of acid, that's what's going to happen. Mn plus 4 is going to go to +7, or sorry, Mn plus 7 is going to go to +4 and stop. Okay, we want it to go all the way to Mn plus 2. Let's look at the answer here. To ensure MnO4 reduces to Mn2 plus, which is colorless. That's what we want to happen. So again, or you could have said to prevent the formation of MnO2, which is Mn4 oxidation state or a brown precipitate. So this is the reasons, okay? Again, I explained that at the time, but you need to find a way to remember that now, okay? So again, I always suggest self-quizzing using flashcards and quizzes, all right? So that's the second, that's the 2 reasons why I added acid. Let's move on. Part C, describe the procedure fully used, and this is a key bit. Again, this is why you need to get really good at reading these answers during the titration. So when you're actually doing the titration, describe fully the procedure to ensure the accuracy of the endpoint. Accuracy of the endpoint. So how do we get an accurate endpoint during the titration? Okay, so that's what we're going to do now. See accuracy during titration. So pause the video and write down some steps that we can do to ensure accuracy during the titration. Not before, not after, during it. What do we do during it? Okay, pause the video and do that now. And then what observation? An observation is something that you see. So what do you see that indicates that the correct endpoint has been reached? So as much detail as you can, what happens at the endpoint that you see that you know it's time to stop, that the reaction is over? So what observations do we see at the endpoint? Write in your answer down for that now, please. Okay, and again, just being careful here that the higher level questions often put 2 little bits together in just a part C, and they don't show you that they're different. It would be really nice if they did this, C part 1 and then C part 2, because you probably wouldn't miss it then. But what happens is that when you're rushing and you're under pressure, you tend to read this, you answer this, and you go, that sound, I'm going down to D now, and then you skip that bit. So it's just about just really carefully reading your questions. Okay, let's go over to the Martin scheme. What things do we have to do? And we need any 4x3. So first of all, we want to be swirling the flask. So as we're mixing, we want to be swirling it. If we're not swirling it, then we're not mixing the solutions together and they're not reacting properly. And you could be gone way past the end point. By the time you pick it up and mix it, you may have way too much added. So you want to be swirling all the time. You want to stop and rinse down the sides of or walls of the flask with the ionized water. So again, I train my students to do that with the wash ball. Actually stop and wash the sides down. What else do we want to do? We want to slow down, add the permanganate, the purple color, add it very slowly at the end by drop or slowly at the as the end point is approached. Okay, and then when you're reading the volume, how much did I use? You want to read the burette at eye level. So actually checking it at eye level, not anywhere else, not from below, not from above. You want to read at eye level. That makes sure that you've done an accurate job. Other ones that you could have had is keep the burette vertical. If it's not vertical, if it's slanted over and you're reading the volume, again, you're not going to be reading an accurate volume. Read the top of the meniscus. That's really weird, but remember that this is that really dark purple colored permanganate. And this is the one chemical that we read from the top of the meniscus because it's very hard to see where the bottom of the meniscus is. And another thing you could do is carry out a rough titration first, so you know roughly where to stop, and then you do it really accurately after that. All right. Actually, I reckon that it would have been quite easy to get 3 there, but it might not have been so easy to get the 4th point. So having a look through this might be something that's worth taking note of. Okay, this question, I've actually only ever seen this come up once. This very question, describe what you do during titration to ensure an accurate reading. Okay, so what do we see at the ends then? Okay, so at the end, remember that the permanganate is self-indicating. So what observation do we make? We see the first pale pink color which remains, or what I say is the first permanent pink color. So permanganate is self-indicating, permanent pink. First permanent pink. Once the pink stays, that one drop that makes it stay pink instead of disappearing or going colorless, that's when the reaction is over. That was only worth 3 marks. Interesting. So indicators normally getting you 9 marks. It didn't on this one because there is no indicator. That was a tricky little section. So just being aware of it for that, especially that bit there, to be looking for 4 scoring points there is tricky. I will admit that. Okay, so maybe that's something that's worth making a note of, that question and that and those answers, what you require in case something like that was to come up again. I think that students may have struggled to get 4 scoring points there. 3 would have been easy enough, but I think getting a 4th one, not so easy. All right, let's move on to the calculation then. The calculation, let's read what it says. It says calculate the number of moles of Fe2 plus in a 25 centimeter cube portion of the standard solution. Okay, so what are they asking us there? To find out how many moles are in, not in a mole per liter of the solution, but in 25 cm cubed. So they're looking for you to find the Fe2 plus in 25 cm cube portions. That's what they're looking for. Now remember that this is the standard solution. This is the one we made up, okay? And we were told that it reacted with the permanganate. So what we need to do here is we need to find out how many moles of Fe2 plus ions were in that solution. Okay. Of course, we know that there was 8.82 grams of the crystals and it was made up to 250. And this is for the iron solution. So we can work out the moles in 250 and we can work out the concentration in moles per liter. And then we need to find out how many moles there are in 25. So if I was to write down the steps that you would need to do here is you want to find the moles of Fe per liter. You want to calculate this and then find the moles of Fe in 25 cm cubed, which is 0.025 liters. That's the steps that we want to do for part 1. So some of us should be able to have a go at this now. I'm going to scroll up and I'm going to show you the piece of text again in case you don't have the exam papers. So what I'm going to ask you to do at this stage is to pause the video and work out what is the how many moles per liter there are of this solution, and then how many moles there are in 250. So pausing the video, oh sorry, how many moles are on 25 cm cubed? So I'm going to get you to pause the video and work your way through that now. Okay, so the first thing that we're told, so I'm writing down, the first thing I know is that there were 8.82 grams of the chemical, 8.82 grams, and that was per 250 mils, per 0.25 liters. Okay, so I always work in liters. I ask my students to do the same. So 250 cm cubed is equal to 0.25 liters. And I'm showing you loads of times how to do that conversion. Okay, so that's what I'm doing there. The next thing that I want to do is find out, well, how many moles per liter would that be? I've got grams over liters here. So I've got grams over liters, which is not what I want at the end. I want moles over liters. Okay, so what I'm going to do now is I'm going to times it by, I need to convert grams to moles here. All right, so I need to convert grams to moles. So I'm using a conversion factor here that goes between grams and moles. So pausing the video and you do the next bit for me. Okay, so what we should have here is grams on the bottom and moles on the top. Grams and moles. Now, of course, the substance is 8.82 grams of this stuff. Okay, so that's the crazy formula we've got to use here to find the molar mass. Okay, so that's the next thing you got to do is work out the molar mass of this crazy thing here. Let's pause the video and do that now. All right, the number that you should be getting is 392 grams. Okay, there's 392 grams for 1 mole. Now, if you were to calculate that number wrong and you were to use a different number, then you would still get that, you would lose 1 mark for getting this number wrong, and you would still get the rest of the marks. But that's only if you show how you work this out. Okay, if you just use the number on your calculator and you put the number in and it's wrong, then you're going to lose a lot more marks. Okay, so it's really important that you always show your work how to find the molar mass of that substance. All right, so once we do that, then we are going to get the answer. And of course, that means we can cancel grams here. We can cancel grams here. And what are we left with? We're left with moles on the top, and liters on the bottom. So go ahead, and I'm going to work this out now. We've got 8.82 grams per 0.25 liters, and then times this by 1 mole for 392 grams. And the answer I'm getting here is 0.09 moles per liter. Okay, so that's 0.09 moles per liter. So that would be moles in a liter, okay? But we didn't have a liter. We were looking for how many were present in 25 cm cubed portion. So how do we go from moles in 1 liter now to moles in, so we're going from moles per liter to moles that are in 25 cm cubed. Okay, so we need liters to cancel. So we're going to cancel the liters there. We're going to times by the number of liters that we were using, which is this here. So let's pause the video and do that now. Okay, so 0.025 liters is the volume we were using. 0.09 times by 0.025, and that gives me 2.25 by 10 to the minus 3, and that's moles. Okay, because liters are gone, we're left with moles. So this is the number of moles that are in a 25 centimeter cube portion here. Okay, right, so we're on to the next bit now, part 2. Of course, that was how many moles are in a 25 centimeter cube portion. That's how much we used in the titration. That's what was in the conical. So now I asked the number of moles of potassium permanganate that were required to oxidize this quantity of iron. So we want to find out how many moles of the potassium permanganate did it react with. Now we need to rely on our equation for this, okay? So we know from our equation there are 5 moles of iron for every 1 mole of potassium permanganate. So with that information, we should be able to go from moles of Fe here, this is moles of Fe, and we should be able to go to moles of KMNO4. So let's pause the video and do that now. Okay, so what we should be doing is rewriting down what we have. We have 2.25 times 10 to the minus 3 moles of Fe. That's minus 3 there, by the way. And we want to times that by, we want to convert, we want to get rid of moles of Fe, and we want to end up with moles of KMNO4. So pause the video now and work through the rest of this by yourself. Okay, so we've got moles of Fe on the bottom, and we've got moles of KMNO4 up top. MNO4 up top. Moles of Fe can cancel with those ones. And then we're going to our equation for the ratio. It's 5 moles of Fe for every 1 mole of KMNO4. 2.25 times by 10 to the minus 3. And then we're timesing this by 1 over 5. And the answer I'm getting here is 4.5 times 10 to the minus 4. And that's moles of KMNO4 now. Or it's actually just MnO4 minus ion that we wanted to work out. Okay, and that is the answer here. Okay, so that's part 2 done. Part 3 then says find the molarity of the potassium permanganate solution. So we know how many moles there were per titration, but that wasn't using 1 liter. That was using a much smaller volume. Okay, so we just have moles, and we want our answer to be molarity, which is moles per liter. Okay, so take this number that we just worked out in moles and put it over the number of liters that it was in. Okay, so you may need to see some of the text above for this. So I'm going to give you a chance to pause the video and see, can you do this now? Take that number and find out what the moles per liter is. So put it in over the number of liters. Okay, so here is the volume that was in of the permanganate. So we highlighted it earlier, but I'm going to rub it out here. It was 20.4 centimeters cubed of potassium permanganate. That was the volume that contained the moles of KMNO4. And of course, we can convert that to liters. So we're going to go 4.5 by 10 to the minus 4. And that's moles of MnO4. And we want to put that over the volume in liters. Okay, so the volume was 20.45 centimeters cubed. We can do some rough work if you want. I'll show you how to do it again. 20.45 cm cubed, and we want to convert that to liters. So put cm cubed on the bottom, liters on the top. The cm cubes can cancel, and now what the relationship between liters and cm cubed? 1 liter for 1,000 centimeters cubed. Okay, so when you do that out, you should get 0.02045. Okay, so now we're going to do this calculation. 4.5 by 10 to the minus 4 over 0.02045 divided by 0.02045. Okay, and when we do that, the answer we're getting is 0.022. 0.022 moles per liter, and that's KMNO4. And that is the final answer for part 3. Overall, not too bad of a calculation, I don't think. The hardest bit would have been getting the first bit started here. I know some of my students have been asking me, is there any way we can, you can give me a list of steps that I need to follow in titrations? And again, obviously this would be handy, and I can do this for ordinary level. But the problem is that every titration they ask these days on the higher level doesn't follow the same format. It's in a different order. I can't just write a list of steps where it's always the same every time. You have to solve problems in these. They're like word equations in maths. Unfortunately, that's just the challenge that they want to put into it. They in the ordinary level, they'll just say, here's the maths, do the maths. And then I can give you a list of steps for them. But in the higher level, I just can't. There's no way of doing that, because I can do it for this one, but then the next one is different. So if you're just trying to learn off a set of steps, it's not going to fly. So you really just have to spend time trying to solve the problems of the questions. And trust me, the more you do it, the better you're going to get at it. But you just have to do loads and loads of these until you've seen all the different kinds of problems before. Okay. Look, I know some students, they'd love to just give me it and I'll learn it and I'll be able to do it. But it's just that it doesn't work in these particular questions. Don't get hung up on it, all right? Look, the calculation here was only 15 marks out of a 50-mark question. You could have got all the other marks, 35, which is 70% of the question, without getting any of the calculation right. So, it's still, students get hung up on this idea that, oh, this bit is hard. And I'm not going to lie, it is one of the harder bits on the course. But, there are ways of still doing very well without this. But that's not to say, oh, forget about it then, because if you're someone who's looking for H1, H2, even H3, then you need to be able to solve these problems. So do stick with them, practice as many as you can. And once you get, like, trust me, once you get used to solving the problems, you'll be able to solve whatever they throw at you. I know it just takes time. All right, guys, that's it. I'll see you in the next one.